Today, we're going to look at this amazing intersection of ancient metallurgy and super advanced AI. We're diving into the world of heat-treated cast iron, a material that's in everything from massive gears to the engine block in your car. And we're going to uncover a really critical lesson about the limits of our technology.
So here's the big question that's going to frame this whole explainer. Why is it that some of our strongest, most engineered materials can still suddenly fail, even when we're using the most sophisticated AI and data to make them perfect? The answer? Well, it gets right to the heart of this constant tug of war between controlling a process and understanding the material itself.
To really get the problem, we've got to understand the solution first. So think about something like a massive industrial gear. It's under incredible stress, day in and day out. You can't just use plain old steel, you have to harden it. The goal is pretty simple: make it stronger, tougher, and more resistant to wear, so it can do its job for millions and millions of cycles without just breaking. The basic process is kind of like a 3-act play. Act 1, you heat the steel way up until its whole crystal structure changes into this high-temperature form called austenite. Act 2, you let it soak at that temperature just to make sure the transformation is totally complete. And for the finale, Act 3, you quench it, you cool it down super fast, which locks in a new, incredibly hard and strong structure. Okay, so check this out, because this is where it gets really clever. One of the best side effects of this hardening process is that it creates a layer of squeezed or compressed material just under the surface. You can think of it like a built-in shield. You see, most cracks start when a material is pulled apart. That's tension. But this layer is already squeezed together, so it's actively fighting back, making it way, way harder for a crack to even get started. All right, so we've talked steel. Now let's pivot to its close cousin, cast iron. It's also really strong, and it's great for casting into complicated shapes. But there's this one little ingredient that just changes the whole game: extra carbon that turns into graphite. So what is cast iron really? Well, it's just an iron alloy that has more than about 2.11% carbon. Think of it like this. Steel is like salt water. The salt, which is the carbon, dissolves completely into the water, the iron. But cast iron? It has way too much salt. The extra stuff can't dissolve, so it pops out as little bits of pure graphite. And the shape of that graphite is everything. And this image, it just perfectly shows what I'm talking about. On the left, you've got this flaky graphite. See how sharp and jagged it is? Those flakes are basically built-in weak points, like tiny microscopic cracks just waiting for a reason to tear the whole thing apart. But on the right, you have these nice, round spheres of graphite. This lets the metal around it stay strong and tough, which makes for a much better material. And here's the key takeaway, right from the source material. Those pointy ends on the graphite flakes, they're called stress razors. They act like little stress magnets. So any force you put on the part gets funneled and magnified right at these sharp tips, making it super easy for a crack to start and spread. Okay, fast forward to today. For years, manufacturers have been chasing this dream of perfect process control, the ability to watch and tweak every little variable in real time to make a perfect product every single time. And now, with AI and all these crazy advanced sensors, it feels like we're right on the doorstep of that dream. So, this is how we used to do it, the old school way. It's all based on decades of real-world data, all packed into charts like this one. You want a certain hardened depth? You look up the right time and temperature. And it works, sure. It's been tested for ages. But here's the catch. It's all based on what happened in the past. It's not reacting to what's happening right now. But our toolkit today? Whoa, it's a whole different league. We have real-time monitoring, simulations that can predict the future, machine learning that spots patterns we'd never see, and even something called physics-informed neural networks, or PINs. The whole idea is to get a level of precision we've never, ever had before. And this is a glimpse into that new world. This simulation is from one of those pins, modeling how a metal solidifies. These models are incredibly powerful, but here's the thing. They can be a total black box. They spit out an answer, but we don't always know how they got there. They learn from data, but they don't, understand the physics of the metal. And that's a really important difference. And this is where things get really interesting. It's the moment of truth. This is what happens when all that perfect, clean data smacks right into a messy, flawed, real-world piece of metal. Which leads us to the big question, right? Even if we control every temperature, every second, every single variable with perfect AI-driven accuracy, can we really stop every single failure? Well, the answer is right here, in this picture of a real part they called cast part A. On the surface, everything looked perfect. It was hardened, strong, wear-resistant, ready to go. But if you look closer, there it is, a crack. And here's the kicker. It didn't start on the surface where you'd expect. It started deep inside. So what gives? When the experts took a closer look at the material itself, they found the smoking gun. Right under the perfectly hardened surface, there was this weird zone with no graphite in it at all. This wasn't a mistake in the heating or cooling process. Nope, this was a flaw that was there from the very beginning, baked right into the material itself. It's like a birth defect in the metal. There's actually a great name for this kind of failure: the eggshell effect. And it's a perfect description. Imagine you have this super hard, brittle eggshell. That's our hardened surface. But underneath, instead of the rest of the egg, there's just mush, no support. The second you put any pressure on it, crack, it just breaks. And this is the whole point of our story. The heat treatment process was perfect. The sensors, the controls, the data, they all did their job flawlessly. But the failure was always going to happen because the material itself was flawed. Your AI, your sensors, they can only control what they can see, and they couldn't see this. Now, does this mean we should just throw out AI? Absolutely not. Not even close. What it really means is that we can't just pick one or the other, data or material science. The future is about mashing them together, using what we know about materials to make our AI and our data tools even smarter.
Let me break down the difference for you. On one hand, you've got your purely data-driven model. That's the black box we talked about. If you don't give it the right data, it might predict something that's literally impossible in the real world. But a physics-informed model, it's different. We actually teach it the laws of physics from the get-go, so its answers aren't just likely, they're actually physically possible. And one of the coolest ways we're doing this is with something called synthetic data generation. So instead of spending a fortune and tons of time running physical lab experiments, we use our deep knowledge of metallurgy, these established theories, to create perfect, massive data sets to train the AI. We're basically using our brain power to make smarter food for the AI to learn from. And hey, this isn't just some theory. The research is already showing that when you mix this synthetic data with just a few real-world experiments for validation, you can cut down on all that physical lab work by like 40 to 60%. That is a huge deal. It saves an incredible amount of time and money. So that kind of leaves us with one final big question to chew on. Our tools, our AI, our simulations are getting unbelievably powerful. But as we saw with that cracked piece of cast iron, these amazing tools are only as smart as the knowledge we build into them. So the real challenge going forward isn't just about building faster, smarter AI. It's about making sure our own fundamental understanding of the stuff we're working with keeps getting deeper and deeper, right alongside.